started. It's a pleasure to have Marc Kamionkowski here today, who almost doesn't need an introduction, but I will try to give an introduction in less than 30 minutes.
Just in case.
Summarize his CV. So he got his PhD in '91 under Michael Turner, where he started his work on dark matter, and then he went to the IAS, and in '94 he became faculty at Columbia. He moved to Caltech in 1999. Where he stayed for about 12 years until he finally ended up at Johns Hopkins. He's won numerous awards for various aspects of his expertise. Just last year, he won the Donny Hyman Prize together with David Spergel, and he won the Ernest Lawrence Award in 2006. And he will tell us about something that he calls astronomy today, which is a little bit off topic of regular work, but I'm sure he'll do a great job. Go ahead.
Okay, thank you very much. I'm very pleased to be able to tell you about dust polarization and interstellar turbulence today. Largely because for the past 6 months, anytime I go to any astrophysics institution, people would look at me and they'd say, do you really think that dark matter is made out of 30 solar mass primordial black holes? And so now I have something else to talk about. And the other thing is, all my life I've been writing papers in which we postulate some new field. Here, I postulate no new fields whatsoever. This is astronomy, pure and simple. Since I am surmising a fairly knowledgeable audience, I'm going to go relatively quickly, also because there's another talk at 2 o'clock, and I don't want to overwhelm you too much. So, I'm guessing that everybody here knows that there has been a long-standing effort to detect B modes in the CMB polarization pattern of the cosmic microwave background. And the goal of this is to look for a signature of inflationary gravitational waves. In the course of making these measurements, it has been apparent, ever since people have begun studying the CMB, that in order to actually detect the cosmic microwave background, you have to distinguish it from other astrophysical sources of emission in the CMB frequency spectrum. And 2 of them in particular are synchrotron radiation from hot electrons in our own galaxy, and also thermal emission from dust in our own interstellar medium. And in principle, these can be distinguished from the cosmic microwave background by measuring the frequencies, by measuring the intensity at many frequencies. So if I have measurements in enough frequencies, and I know something about the spectral dependence of synchrotron and thermal dust and the cosmic microwave background, then I can separate them out. And in particular, Planck had one channel at 353 gigahertz, which is pretty far out on the wean tail of the cosmic microwave background. And so to a very good approximation, this 353 gigahertz map gives us a map of the distribution of dust in our own galaxy. And of relevance for this particular talk is the fact that the 353 gigahertz channel on Planck is polarized, so they can actually measure the polarization Stokes parameters Q and U at each point on the sky, as well as the intensity, which will also be important. And this is now a done deal. Here are the measurements. And I show these to you to impress upon you the fact that they have measured the polarization over a very good fraction of the sky, and with pretty good angular resolution and pretty good sensitivity. This is the polarization magnitude, this is the polarization angle as a function of position on the sky. This is interesting for those who want to study the interstellar medium, because the interstellar medium is magnetized, and the dust grains that are doing the emission at that are producing the emission at 353 gigahertz are spinning in the magnetic field, and that spinning tends to align them in a direction perpendicular to the magnetic field. And for a variety of reasons that are straightforward, you wrote the first paper on this, did you? One of the first papers?
It's never straightforward.
So for reasons that are too complicated to explain right now, it shouldn't be too much of a surprise that if the dust grains are aligned perpendicular to the magnetic field, that the polarization is perpendicular to the magnetic field. And this is not just theoretical speculation. There are good reasons to believe this empirically. So we have a polarization map of thermal dust emission across a vast regions of the sky. And it might be interesting to ask whether we can study it. So the way we study a polarization map is shown here. So we measure the Stokes parameters Q and U. But these are components of a spin-2 field. The values that we obtain for q and u in any given direction are specified with respect to some x, y coordinates that we provide on the sky, or that we specify in the sky. They are not rotational invariants. If we choose a different coordinate system, the values of q and u will change. But as some of us showed 20 years ago, if you have a polarization map, you have q and u that are provided to you. You can write down a complex polarization, q plus iu, and then you can Fourier transform it and get the Fourier coefficients q sub L and u sub L. And then if you do this very simple manipulation on a flat sky, it's really, really easy. You take q plus iu, you multiply by e to the minus 2i psi sub L, and psi sub L is the angle between the Fourier wave vector L and the x-axis. These things, these e's and b's that you obtain in this way, are rotational invariants. Here is a picture of an E mode for a given wave vector L in the horizontal direction. In the E mode, the polarization varies along directions parallel and perpendicular to the direction of the Fourier wave vector. And for a B mode, the polarization varies along directions 45 degrees with respect to the direction of that particular Fourier mode. So that's how you can distinguish an E mode from a B mode. So we have the map. We have q and u as a function of theta. We can do a Fourier transform, get q and L, u L. You can get E and B. And then the next thing that we often do is calculate the power spectrum. So the power spectrum is a function only of the magnitude L, not its direction. And C sub L EE is the average value of all of the modes E sub L, E sub vector L, where the vector L has a magnitude L. So we take all Fourier modes that have the same magnitude, pointing in all directions, and we square them and take the average, and that's C sub L EE, and that's C sub L BB. So before Planck, polarization results in 2014 were announced in September of 2014. Theorists had constructed a variety of models for dust polarization that they expect to see on the sky. And the pre-Planck dust expectations, all of the models that you can find, and this goes back to a paper by Matthias in 2001 where he explored polarization patterns that might arise from supernova remnants. O'Dea et al. Is a collaboration of 3 people that tried to construct a state-of-the-art dust polarization map from all available information. De la Bruyere et al. Was the Planck certified pre-Planck dust polarization model. And there's also a paper by Eli Kovats and I where we developed statistical techniques to separate foreground from CMB, and in that, our techniques, in this paper, we assumed that C sub L BB was equal to C sub L EE. And you can, the expectations come from any of a number of arguments. So if I have a random polarization field, I just generated a random polarization field, there'll be random power, equal power in Q and equal power in U, and E and B are just some linear superposition of those, so you get equal E power and B power. If dust is randomly distributed but is in a uniform magnetic field, and we've all seen maps of the magnetic field of the galaxy, and there seems to be some large-scale coherence in those magnetic fields. And so if dust is distributed randomly in that magnetic field, but the polarization is always aligned with the magnetic field, you also get equal E and B. And I have a few slides to show that, but I'm not going to go through them right now because, as I said, I'm trying to give an abbreviated talk, but I can go through them afterwards if anybody wants. So Planck made their measurement. September 2014, they announced the results. And this was what they found. C sub L EE is about twice C sub L BB. So here is a picture. So they don't measure the E mode power spectrum over the entire sky and the B mode power spectrum over the entire sky. They split the sky into a bunch of different patches, several hundred small patches on the sky, and then measure the E mode power and the B mode power in all those different patches. And you see there's a lot of scatter, and the fraction, the B to E ratio, is not measured very well in some places. Some of the scatter may be due to noise. Some of the scatter may be real. But on average, it's roughly 1/2. And in particular, in the best measured places, where the error bars are smallest, it's pretty damn close to 1/2. It's also true at high galactic latitudes and also at low galactic latitudes. Although most of my interest is at the high galactic latitudes. So H, do you know this? So I asked everybody when this came out. So I should say that this went largely under the radar because when Planck announced results in September 2014, everybody was so focused on bicep 2 that they completely ignored the dust polarization science. But I started asking around, do you know why E is twice as big as B? Do you know why A is twice as big as B? No, no, no. I started playing around with a couple of postdocs and students, writing down toy models. It's not easy to get. I went downstairs and I asked Chuck Bennett if he knew. He goes, oh yeah, we knew that. It was in WMAP. So it turns out that the synchrotron power at lower multiples than those probed by Planck, primarily, also seems to have there also seems to be twice as much E mode power as B mode power in the synchrotron, although it's not as well determined, given the statistics and noise, as in Planck. So this is the question, which stands for, whence the 2 factor? So, why is this 2? And I should say, before I go on, that 2 is an interesting result. The null result, the expectation, was 1. And everybody expected 1. There is no pre-Planck paper that you can find with a theoretical model where they say E over B should be 2. And so this is an interesting question. Something is going on in the interstellar medium to set this factor to 2. The other thing I want you to note is that the temperature polarization cross-correlation was measured by Planck and found to be positive. I actually sent an email message to the person in Planck most responsible for this to check the sign. The sign is important. The magnitude, for our purposes, the magnitude compared to what I'm going to talk about has not actually been calculated precisely, but is definitely measured. It's measured to be positive with very, very, very significant statistics. So the Planck papers that actually study the dust polarization and all of the literature discusses the polarization pattern in terms of interstellar turbulence. So why is that? The interstellar medium has a very large Reynolds number. That means that the viscosity is very small, and so if you stir up the fluid, there will be very rapid cascades of large-scale motions to smaller scales, and you expect the distribution of fluid velocities and densities to acquire that of a turbulent fluid. That means that it should acquire a Kolmogorov spectrum. So E of k is the energy in Fourier modes with waves numbers between k and k plus dk. And that Kolmogorov spectrum is k to the minus 5/3. And it's a very easy and elegant thing to derive. Kolmogorov did this, many years ago. And the basic idea is that if I stir a fluid on large scales, those large scale motions will cascade to smaller and smaller scales. And in steady state, there will be a constant flux of energy from these large scales to the small scales. And with that information alone, it's a few lines to derive E of k proportional to k to the minus 5/3. I should say that this Kolmogorov spectrum is derived for an unmagnetized fluid. But, it's a simple guess. And the energetics are no different in a magnetized fluid. And the other reason why interstellar turbulence is generally assumed to be what is explaining the dust polarization is empirical. So people who study the ISM have plotted this thing they call the big power law in the sky. So they can infer the electron density fluctuation amplitude as a function of wave number through various techniques. For example, interstellar scintillation, etc. And this electron density power spectrum is determined over many orders of magnitude, and it's very consistent with a power law over many orders of magnitude with a power law index that agrees with that you expect from a Kolmogorov spectrum. So that's another reason why we discuss interstellar turbulence. As I said, though, the interstellar medium is magnetized, however, and so it is not an unmagnetized fluid. Well, that's kind of a tautology. So it is described as a magnetohydrodynamic fluid. So if you have a plasma and there are magnetic fields in that plasma, the magnetic fields are tied to the plasma. So if I have a magnetic field in this direction, the fluid wants to move in this direction, the magnetic field lines move with the fluid. And there's a difference between it's easier for the fluid to move this direction, along the magnetic field lines than it is across the magnetic field lines. And so as a result, the turbulence is not necessarily expected to be isotropic. You expect there to be some anisotropy in terms of the excitation of Fourier modes perpendicular to the magnetic field as opposed to parallel to the magnetic field. Another interesting fact is that the magnetic Reynolds number, which sort of tells us the magnetic equivalent of the viscosity, or the viscosity for a magnetized fluid, is also large for the interstellar medium, and so the magnetic fields aren't going to quench the turbulence, but the turbulence is expected to be MHD turbulence rather than unmagnetized fluid turbulence. So in the process of preparing this work, I started to read lots of papers, and what I inferred is that they are complicated. This is the only true statement that I know how to make about MHD turbulence. It is complicated. There are about 50 years of theoretical work on the subject, about 20 years of detailed numerical simulations. There are still many theoretical uncertainties. There are still many questions about the detailed predictions of MHD turbulence models. The point of the models, though, is to tell you how the different Fourier modes of the MHD fluid are populated. And although people disagree about the details, it's believed that the basic scaling is probably the same as in the Kolmogorov spectrum, but you expect the turbulence to be anisotropic with Fourier modes perpendicular to the magnetic field, preferentially excited. I'm not going to say too much more about the details of MHD turbulence, but I will say a little bit about magnetized fluid perturbations. So we have a magnetized fluid. We want to consider the most general perturbation to that magnetized fluid. And the most general perturbation to a magnetized fluid can be decomposed into three different modes. And the reason is that there's a magnetic field. A magnetic field is a vector, h, but it's divergence free, and so there are two transverse vector degrees of freedom associated with the magnetic field, but there's also a plasma density, and that gives you an additional degree of freedom. And so the combined magnetized fluid system has to be described in terms of three normal modes. And those three normal modes are called slow, fast, and Alfvén waves. And the weak field limit, where the magnetic field is weak, when the magnetic field pressure is small compared with the fluid pressure, the fast waves approach a sound wave, and the slow Alfvén waves approach transverse field perturbations. But more generally, for arbitrary beta, this is a parameter that we use to describe the MHD fluid. Beta is the ratio of the gas pressure to the magnetic field pressure. So large beta is weak field, small beta is strong field. So for more general beta, the slow and fast waves are some combination of plasma density and transverse field perturbations, but the Alfvén waves are always transverse field perturbations and therefore involve no plasma density perturbation. So what Chris Harada, Robert Caldwell, and I did is we calculated the polarization pattern induced by any of these three different particular Fourier modes. So in particular, we assume that the line of sight is the z direction. We then consider a Fourier mode of one of these three different types in the plane of the sky. And then we suppose that there's a background magnetic field that points in some direction, which you take to be in the xz axis. So the magnetic field can be perpendicular, in the plane of the sky, or it can be perpendicular to the plane of the sky. And then what we do is we calculate the polarization pattern induced by each of these three different types of waves, slow, fast, and Alfvén waves. And if you look at the paper, the equations are long, but it's perfectly straightforward. So what we do is we calculate the complex polarization, Q plus IU, and we assume that the complex polarization is equal to some constant A, which we take to be negative, so that the dust polarization is perpendicular to the magnetic field. N is the number density of the emitting dust. So there'll be more polarization where there's more dust. And then this quantity here, h sub x plus I h sub y squared divided by h squared, just tells us that the polarization will be perpendicular to the magnetic field orientation. So this, as I said, we consider a background magnetic field in the xz direction. So we consider then, as I said, we consider an individual Fourier mode of the slow, fast, or Alfvén wave, and then we calculate the polarization pattern Q plus IU, we do the appropriate transformation, and we get the E, B, and T amplitudes for this particular mode. Yep?
Are you assuming the dust polarization is always perpendicular to the instantaneous direction of the magnetic field?
Yeah.
Is that reasonable? And how long does it take to realize?
I'm guessing, I don't know, I have not been asked this question before. I'm guessing that with pencil and paper we can infer that the alignment time is much shorter than the time scale for the magnetic field to change. But also empirically, it seems to be the case. And I'll talk a little bit more about this later. So the next thing we do is then average over all background magnetic field orientations. And there are two reasons we do this. It's reasonable to surmise that the background magnetic field in this region of the sky might point over here, and then in some other region of the sky might point in some other direction, some other region of the sky might point in that direction. But averaged over the entire sky, it should average, there should be no preferred magnetic field. The other thing is if you look at the synchrotron radiation, the polarization fraction for synchrotron radiation is far less than it would be if you had a single magnetic field direction along a given line of sight. And so we surmise that even along an individual line of sight, there are several different background magnetic fields contributing. So we average over all background magnetic field orientations. We then make predictions for different spectra of slow, fast, and alphane waves. And we do so for two parameters, two parameter family of models. One is beta, and the other parameter is lambda. And lambda describes the anisotropy of the power with respect to the background magnetic field orientation. So if lambda is 0, then the power in slow, fast, and alphane waves is isotropic. If lambda is positive, it's aligned with the magnetic fields. If lambda is negative, it's perpendicular to the magnetic fields. And all I need to tell you, all you need to know for now is that MHD turbulence models seem to suggest that the power, that lambda should be negative. How negative, I don't know, but if anything, lambda should be negative. And then I should say that the different MHD turbulence models, well, let me show you what we did. So here are the results of our calculation. So we calculated the E to B ratio and the temperature polarization cross-correlation coefficient. The reason we calculate the coefficient is that the cross-correlation itself depends on unknown polarization fraction. But if we scale up, if we calculate this cross-correlation coefficient, which is TE divided by square root of TTEE, that polarization fraction cancels out. And that makes the results in some sense more robust. So here we have it. So this is the E to B ratio contributed by alphane waves, by fast waves as a function of lambda for values of lambda negative. We don't show lambda positive because it turns out there isn't any lambda positive that actually does any better. And you can see that you can get E over B of 2, but you can also get E over B less than 2. The fast waves have a particularly fast dependence on this anisotropy parameter. Over here, for example, the slow and fast waves allow you to get E over B close to 2, but the slow waves give you a very negative TE. Now, MHD turbulence models make specific predictions for the relative populations of slow, fast, and alphane waves. And we have not actually taken the final step of taking an MHD turbulence model and figuring out exactly what it predicts for E, B, and TE. But we have actually done a by-eye analysis. And what we infer by looking at this, and we've talked with several MHD turbulence people, and they seem to agree that our assessment is not too bad. Our conclusion is that there is no MHD turbulence model, no combination of parameters lambda and beta that you expect from a turbulence model that actually allow you to reproduce E over B equal to 2 and a positive TE cross correlation. And so one of the things that we infer, although we're not going to claim that this is an absolute final demonstration, one of the things that we infer is that this data suggests that there's something beyond MHD turbulence that is accounting for the dust polarization pattern in Planck.
Is there any measurement of the plasma beta at least?
Of what?
The plasma beta that the ISM actually has, is that measured in any way?
I don't know. There are some comments in an Alex Lazarian paper that say that beta of 0.1 is probably what's going on, but I can't figure out where that statement comes from. And I don't even think that you'd expect there to be a value of beta, because the interstellar medium is two words, but it's a very complicated system. If you actually look at the maps, there are huge variations in the intensity and the polarization from one region of the sky to another. So I don't even know that there's one beta. So it may be possible that by averaging over different values of beta and different values of lambda, we could get the appropriate result. But we've thought about this, and it's not easy to do so.
It depends a bit on what you call the gas pressure.
Yeah.
Because the thermal gas pressure is low
Yes. Yes.
Because of the large scale motions. And I think if you take it relative to the turbulent gas pressure, I mean, the turbulent magnetic field is driven up, it's said, by NHT turbulence.
Yeah.
Towards partition.
Yeah. So let me tell you something else. Yep.
Here, your matter calculations, so the magnetic fields are frozen to matter, correct?
The matter fields are
The magnetic fields are frozen
in the plasma.
in the plasma.
Yeah.
And you also have density calculations. So these density calculations are potential, in a way it's a curve-free.
Let me get to that.
velocity fields are curve-free.
Let me get to that.
Okay.
I didn't say anything. No, the velocity fields are not curl-free. But I'll say something about that in a second. So there's another important piece of information. The spectral index for the EE, BB, and TT power spectra are measured very precisely by Planck, and all of them are very, very close to minus 2.42. And this is quite a bit different than the value, minus 3.67, you would actually expect for a Kolmogorov spectrum. And so we think that this is another indication that MHD turbulence is not, the appropriate description or the appropriate physics to describe the dust polarization maps. So what we surmise is that what we might actually be seeing is not the Kolmogorov spectrum, not the turbulent cascade, but we're looking at distance scales that overlap the distance scales over which the turbulence is stirred. So you get a turbulent cascade if you take a fluid and stir it on large scales. That turbulent cascade then goes to smaller scales, and on some very small scale, you hit dissipation. So the big power law in the sky that we see for electron density fluctuation sort of covers this range, but the distance scales probed by Planck, dust polarization maps, are probably on order 0.1 to 30 parsecs. And that is sort of a bit larger distance scales than is actually determined by interstellar scintillation and other measures. And so what we speculate is that the dust polarization maps, Planck dust polarization maps, are probing something having to do with the large-scale physics that stirs the interstellar medium, rather than the turbulent cascade to smaller scales. What that large-scale physics is, we don't say, we don't know. It might be supernova winds, it might be stellar winds, it might be galactic spiral shocks. We don't know. We did go one further step, and we developed a simple phenomenological model. This is actually a cut and paste. I took a screenshot of the equations from the paper. So this is the extent of the model. It's very simple. So what we did is we supposed that we have a homogeneous, unperturbed magnetized fluid with a magnetic field that's pointing in some direction. And then we consider an arbitrary perturbation, which we describe by a displacement delta as a function of x. So at each point in the fluid, we move the fluid a little bit, and we assume that the magnetic field goes with it because it is a magnetized fluid. So delta, we then assume, is so it's straightforward. If you make the simple assumption, you can calculate the density the dust density fluctuation just from the continuity equation. And you can also calculate the magnetic field perturbation associated with this density perturbation by the MHD equation, the equation that tells you the magnetic fields move with the plasma. So it's perfectly straightforward. We then assume that delta is a random field, is a random displacement field with a nearly isotropic spectrum of fluctuations. And then we find this. So this simple model gives you an E over B of 2 for a relatively small anisotropy parameter, -1. It's also a fairly slowly varying function of lambda, and so it doesn't require a very specific value of lambda to get the correct answer. The TE cross correlation is positive. And the last thing I'm going to tell you about this is that this vector field, this three-dimensional displacement vector field, can be decomposed into a longitudinal component and a transverse component. This is the answer to your question. And it is the longitudinal component that's providing a large E over B. It's a longitudinal component that's providing a large E over B, and a pure transverse displacement field would not do the trick. The other thing to keep in mind is that it's the slow and the slow and fast waves that are producing the cross correlation, not the Alfvén waves. And this plot shows you the E and B mode powers as a function of the anisotropy parameter. And you can see how much power is contributed by the parallel components and the transverse the longitudinal components and the transverse components. So this is not a physical model, but it's a very simple mathematical model. And what we're surmising is that whatever physical model is actually describing this interstellar turbulence has to fit this mathematical structure. Something is exciting longitudinal modes in the plasma at large distance scales.
Yeah, so before your MHD calculation, what did you put in for the velocity?
For the velocity?
Yeah.
Oh, so I mean, the MHD turbulence doesn't care what's stirring it. That's just, the MHD turbulence is just the cascade to smaller scales. So we don't.
What are the initial conditions? Well, the independent initial conditions you have some modesty or one plasma.
No. Well, we looked at the literature. We tried to understand it. I went to Ethan Vishniak's office. I said, this is what I think the papers are saying. He said, yeah. So what the papers are saying is there are fast waves and slow. There are slow and Alfvén waves. The papers say the slow and Alfvén waves have comparable amplitudes, and they're expected to be pretty anisotropic, especially on small scales. And the fast waves, the amplitude of the fast waves has nothing to do with the amplitude of the slow and Alfvén waves.
So if you are sound wave dominated regime, yeah.
This will, well, it depends on beta. It depends on beta. If I'm in a weak field limit, then a sound wave dominated regime should look like this. Yes.
Mm-hmm. Yeah.
That's right. So there are any of a number of caveats. You know, this is not a simple and elegant cold dark matter model with small scale linear fluctuations. The ISM is a very complicated system, and so there are a huge number of caveats. The one that we thought a bit about is the assumption that we make that the dust density traces the plasma. So everywhere we've assumed that the dust is tied to the magnetic fields, but it's the plasma that's tied to the magnetic fields. And there are three theoretical arguments that we can make. If you just calculate the mean free path for a neutral dust particle to run into the plasma, that mean free path is longer than the relevant distance scales. But if the dust particles are charged, then they might actually have gyro radii, which are small compared with the relevant distance scales. So we actually can't prove one way or the other theoretically whether it's correct. Empirically, though, we think there are a number of reasons to believe that dust does trace plasma to some degree. Quantitatively, I don't know precisely how much. But if the dust was randomly distributed, we would have equal E and B mode power and no TE cross correlation. If the dust were randomly distributed, you would see no synchrotron dust correlations, but there are indications from WMAP and Planck that the synchrotron radiation, the synchrotron and dust are correlated, and in polarization too. You also see this E over B ratio in synchrotron radiation. You also see it in these H1 alpha maps. I just talked to Susan Clark, a graduate student at Columbia, yesterday about this work that she's done. And it's interesting because what they measure is actually different than this. So the fact that they're getting E over B of 2 is not a confirmation of Planck. It's actually some additional piece of information. There's also very good agreement between 21 centimeter maps and dust far infrared maps. So we believe that this assumption that we made is warranted. But quantitatively how good it is remains to be determined. So there are lots of interesting questions for further work. So let me summarize very quickly, and I'll tell you one more thing. This E over B ratio of 2 was a complete surprise. Nobody expected it, and it is interesting. It is not null results. Whether our interpretation of MHD, the implications for MHD turbulence are correct or not, I think the most valuable thing about what we've done is that we figured out how to read these dust polarization maps. There's information in those E and B modes about the composition of the population of slow, fast, and Alfvén waves in the interstellar medium that cannot be obtained in any other way, as I understand. We said we're going to calculate E and B we calculated E and B ratios and TE cross correlations for averaging overall background magnetic fields. But in some regions of the sky, you might actually have a very strong particular magnetic field, background magnetic field. And in that patch of the sky, you might expect E over B to be something else and TE to be something else. And you might also expect the power in that patch of sky to be anisotropic. So this is something we can do. We can look at all these small patches of the sky and see how the E over B, the power anisotropies in the TE, vary as a function of position in the sky. This outer scale hypothesis that we made, that we're overlapping the outer scale of turbulence with the dust polarization maps, implies a departure from scale invariance in EBT, dust power, in the dust power spectrum, larger and smaller scales. So maybe class will see a turnover at large angular scales. Maybe with better measurements at small angular scales, we'll see that the power law index begins to approach the minus 3.67 expected for turbulence. And the other thing is that these tools that we've developed, which here we just discussed, in terms of the Planck dust polarization maps, these tools can also be applied to high-resolution polarization maps of individual molecular clouds. So you can go to an individual molecular cloud, get a polarization map, and the tools that we've derived can be used to tell you something about the state of the ISM, the magnetized ISM in that molecular cloud. And it's actually been a lot of fun for me the past few months, because I've been talking to lots of people who actually know something about astronomy and learning all kinds of interesting things. There are lots more that we can do with forthcoming projects. Planck was this huge satellite mission. It took 20 years, but we don't need Planck to make a huge amount of progress on short timescales. A lot of what we would like to know can be obtained by deep integrations on small regions. So this is a perfect science target for experiments like BLASTPOL before PILOT. So this is a paper by Eli Kovats and I that made a fairly obvious point, simply that you could take essentially off-the-shelf hardware and integrate deeply in a small region of the sky and learn far more about the dust polarization emission on that small patch of sky than you could from Planck. There are implications for large angle measurements. So there are interesting things that class can do. To, in particular, if we're looking at the outer scale, then there should be a rollover in the power law index for the dust and synchrotron at larger scales. There's a whole array of new science targets for CMB S4 and also for Simon's array, BICEP, Keck, SPT pole, ACT pole, etc. So interestingly enough, the CMB S4 science book has only cosmology in it, but there's another chapter that you can write with a whole bunch of interesting ISM science that you could do. Sorry? We can get extra money. The Department of Interstellar Research. Oh, you might be able to get some. We're going to do the Starshot thing, right? They got to know what kind of magnetic fields they're going to be flying through. So.
Well, if you don't know this stuff, then you can't actually do the art science. So it is fundamental.
Yeah.
So we have to sell it.
Yeah. I think I said this already. There are interesting things to do with H1 maps. There's this paper by Susan Clark, Josh Peake, Colin Hill, Mary Putman. And I had seen the paper before, but I only read it carefully a few days ago. And it's a really nice paper. And it's very rich. And as I said, they measure an E over B ratio of 2. But what they're actually measuring is different than what Planck dust polarization gives you. And I have to think more about what it actually means. And of course, those of us who are interested in the early universe are going to have to separate these foregrounds, the cosmic microwave background that we're interested in, from the foregrounds. And I don't have anything in particular to say about this, but I think it is pretty clear that the better our understanding of the interstellar medium, the better our ability to develop good component separation algorithms. So that is all I have to say. Thank you very much.